All right, guys, welcome to another episode of Cuda Education. We are on the compute example as we continue. The purpose of this video is to talk about Q families. Let us just run the application and get started with what's going on. So we have an example where we supposedly input a bunch of numbers, but we input a bunch of numbers on the CPU. We create a bunch of numbers, an array of 32 numbers on the CPU. We use a staging buffer to transfer those numbers to the GPU. The GPU does some computation where basically it takes the first two numbers, adds them together to get the third number, and basically every number after that is a summation of the two previous numbers. So 0 and 1 makes 1, 1 and 1 makes 2, 2 and 1 makes 3, 3 and 2 makes 5, 5 and 3 makes 8, 8 and 5 makes 13, and we continue. Okay, the input isn't really necessary, but it's done to demonstrate transferring data from CPU to GPU using the staging buffer, right? Once the calculation is done on the GPU, the results are transferred back to the CPU and displayed on the screen. This is a compute example, which basically means there is no graphics capabilities with it, right? There's no graphical capabilities on the GPU side. There's no swap chain, there's no rendering, there's no drawing, anything like that. The computation is done on the GPU, but then it's transferred. The results are transferred back to the CPU, for which the CPU will display to the screen. Notice that the display to the screen is very rudimentary, like DOS-like, right? Command prompt-like. There's nothing special, and that's because it's a CPU generating to the screen, and there is no special anything, right? I assume the CPU has some kind of integrated graphics thing that even does this, but you get my drift. So this example is a dedicated compute example, minimal headless compute example, right? So the purpose of this thing is that we want to discuss the Q family. So the way how it's done is that we withdraw the Q family properties of the GPU and then cycle through all of the Q families to find one with compute capability. So if Q family index it has compute capabilities, we choose that index and proceed with our application. We have to do it this way. We have to do it with a for loop and all of that and this production, because the author of the application does not know what environment this is going to be run on. Remember, Vulkan is supposed to run on many different devices. It's portable, right? That's the selling point of Vulkan. It can run on Unix, Windows, Linux, Mac OS. It can run on AMD GPUs, Intel GPUs, NVIDIA GPUs, you name it. It can run on So in order for, nothing can be hard coded. You have to basically request the properties of the GPU, cycle through all of the properties, and then choose an index that represents the compute capability. On my GPU, it could be index 1. On an Apple GPU or an Intel or AMD GPU, it might be index 5, okay, or 2 or 3 or 0, whatever, right? So we have to do this inefficient process of cycling through all of the properties until we find one that has the properties that we like. So this is basically the situation. So um, what I want to do now is update the I want to update the I want to update the algorithm to basically I want to update it so that we get a list of Q families on our. Okay, we get a list of Q families on the system. Okay, so we have, I'm running a GeForce RTX 4050 laptop GPU. We have six families: family 0, 1, 2, 3, 4, 5. Each one of these families has different capabilities. Okay, so we have different capabilities. For family 0, we have graphics, compute, transfer, and sparse. All of them have transfer and sparse. So, I'll negate to mention those. Family 1 has just transfer and sparse. Family 2 has compute, transfer, and sparse. Family 3 has transfer, sparse, video decoder. Family 4 has transfer, sparse, video encode. Family 5 has transfer, sparse, optical flow. Now, the thing is, um, these families also have what they call a queue count, which basically means how many simultaneous uh, threads of submission, or how many queues can I line up, how many submissions can I line up simultaneously for each of the families. For family 0, we have 16, family 1, 2, family 2, 8, family 3, 1, family 4, 1, and family 5, 1. Notice that for these 3, 4, and 5, we have a queue count of 1, and there's a reason for that, which I'll get into in a second. So we have all of these families, and we have all of these. We have the graphics and compute on one, and we have the dedicated compute queue on family 2, right? So if we go to where is it? Oh, it's up here, right? If we go to our queue if we go to our queue if we go to our queue selection piece, now we have if compute and not, notice the exclamation, graphics, right? So we have if compute and not graphics. We want a compute capability, but we also don't want graphics, right? um, Let us actually, well, since I have it up, so we want compute and not graphics. Okay, so which one has compute and not graphics? This one has compute and graphics, so it's out. Family 0 is out. This one doesn't have compute, so this one is out. This one has compute and not graphics, so family 2 is probably the one that was chosen. Families 3, 4, and 5 don't have compute at all, so those are out. All right, so notice that for family 2, we have a queue count of 8. Okay, so there are 8 simultaneous submissions that we could make for family 2. And if we look down here, requesting 8 queues from family 2, compute, transfer, sparse, right? So these are the handles for all 8 queues into family 2, family queue 2. Okay, so that's how we know that this was the correct one. Now if I take out graphics completely, right? If I take out the graphics requirement completely, and then close out our thing and then run it back, we basically are going to get um, we're going to get 16 queues, right? So we have from 0 to 15, we have 16 queues, right? And that basically family 0, and that matches up with what we have here. And that makes sense because the for loop starts from 0 and then works its way up. So it sees that this one has graphics and compute. It's like, okay, we're going to use this one. All right. So that's how we do that one. We could also, so if I re-put back in the requirement, it would basically do the dedicated compute, right? So we have to now get into a discussion of we have to spend some time with this guy right here. Okay, so we have 6 families, different things happening. Okay, so notice that we have a dedicated compute. They all have transfer sparse, so we don't even have to mention those. Actually, let me just quickly. So this one is a dedicated transfer family. Family one is a dedicated transfer one. Okay. Um, that's the one that's dedicated to transfer. I notice that it has a queue count of two. Okay. Uh, family three, four, and five. Family three is video decode. Family four is video encode, and family 5 is optical flow. Notice that these only have a Q count of 1. Okay? These only have a Q count of 1. Now, what you guys have to understand is that this conversation is basically somewhat trying to mimic what is the hardware realities of the GPU. So I'm talking chips and circuits and physical, the actual physical layout of what's available on the GPU, right? Vulkan API and software in general is literally an abstraction, right? But to a certain extent, these Q families are trying to mimic what is actually going on the hardware. So we'll get into that for in a second. But notice that we have the graphics compute transfer sparse. Family zero is the Q family with the most Q counts. Okay, and it has 16 channels. Right. This makes sense. This makes sense because first of all, it's a GPU, right? Second of all, most people buy GPUs in order to do graphics stuff, right? There is also a push to get GPUs to do a lot of computation because of the parallelism of GPUs, right? But remember, guys, whenever you hear GPU, you're trying to figure out how much graphics can it push, right? How great is your GPU and how much frames per second can you generate and stuff. So naturally, you're gonna find that the graphics Q family is going to get the most attention and have the most capability in terms of the Q count that it allows, right? So in our case, it's 16. Now notice that with graphics, this is the only Q family that has graphics. There is a Q family that's specialized in compute, right? So compute has its own sort of world, but graphics is tied to compute, right? Now this makes sense because on a hardware level, literally, graphics is basically, if you dive into what graphics is, it is computation on the back end, and then in the front of the hardware. So it's like think of a piece of hardware that's for graphics. On the front end of it, it has some sort of fixed function, dedicated graphics, you know, operating stuff, right? So on the front end, it's a lot of like fixed function stuff that deals, specifically for graphics. But on the back end, it is compute also, right? So implicitly graphics has compute, and for obvious reasons. I mean, you have to calculate stuff when you're dealing with graphics, regardless of how you want to slice it. So on the front end, you have like fixed function operations, like mathematical operations that is specific to graphics, but on the back end you still have compute. And that is why in family zero you have the ability to do graphics and you have the ability to do compute. And what happens if you request a compute work on family zero? All it does is just skips the front end fixed function stuff. It skips the front end fixed function graphic stuff and just goes straight to the compute cores. But you also have a dedicated compute family 2. And notice this has 8 Q counts, right? So you could do 8 lines of work on this dedicated compute thing, right? Now, am I gonna say that this hardware here is superior to this hardware here? I'm not in a position to say that, right? I don't know. I don't know. Maybe, but I don't know. Like, can family 2 do compute better than family 0? I don't know, right? Um, but what we do know is that if you have stuff that you want to compute, right, and you don't want to do it in the same place where you're doing graphics, because you're doing, remember, GPU is fast processing, it's parallel processing, it's high performance computing. You don't necessarily want to hold up the graphics portion of the work with compute work. So if you could offboard the compute work onto a separate queue family and just have this dedicated to doing graphical stuff, then it possibly could make your application better. The only thing that is problematic possibly when you do this is, are there dependencies between graphics and compute? So you could talk about offloading all the compute work you want, but do you have to synchronize with graphics? If you have to synchronize with graphics, if you have to wait for graphics, if you have to wait for results from graphics in order to continue computation, or to have a deciding factor, a fork in the road, and you need the results from graphics to do it, then it complicates matters, right? So it's not like you could just offboard all the compute, have it run on its dedicated queue family too, right? And think that you've automatically won. It's not that simple. I mean, yes, if the two processes, if graphics and compute are completely independent, sure, you could do that, but that is not always the case. So sometimes it might be better for them to share the same queue family. Other times you might get away with offboarding it onto family two, right? But you don't know. The only way you could know, and the reason why this is such a big deal in graphics, in computer graphics and high performance computing, the only way you could know is if you profile, right? If you do profiling, you run your application through a profiler, you get back data on what work is being done where, how is it being done, how much time is it taking, is the GPU idle, or is it overloaded with work? What is overloaded with work on the GPU? What time is it overloaded? What sub process is causing overloading, or what sub processes is causing idle time, or what is being waited on for the idle time to happen? All of these questions. The only way you could really do it is if you use a profiling tool. Now, if you have an NVIDIA GPU, there's a piece of software called Nsight Systems that basically is a profiler. Anytime you hear high performance computing, the next thing is, what's your profiling tools like? You need to be able to profile your application, right? Because you need to know, should I keep this on the same queue family, or should I offload compute onto a different queue family, right? This is all, there might be a mix and match, depending on synchronization, depending on dependencies, memory dependencies. You also have to deal with bandwidth, right? Memory considerations. So notice that all of these queue families have transfer capabilities, which again is dealing with memory, right? Because you have to feed compute and you have to feed graphics with information, with data, right? And even once the data is being processed and produced, you still, you now have to transfer that to other parts of your application or other things, and all of that stuff. That could be another bottleneck. So it becomes a very messy situation, right? It is also the reason why, you know it's easy to understand that you need compute stuff. You need to calculate stuff before you present it, before you do graphics, right? You need to compute, what are the vectors, where are the vectors, is the vectors transforming because the ball is rotating, or the rock is rotating in space, and you need to translate and rotate and move the geometry and all that stuff. It's easy to understand. You have to compute stuff and then present to graphics, right? So graphics is a consumer of the things that compute, the products of compute. But conversely, compute is a consumer of the things that graphics produce. This is a little bit intellectually harder to understand, but there's things like stencil test, depth test, Z buffer. Whether an object is whether an object is visible by the camera, by the user. So if an object isn't visibly seen by the person playing the video game, or the person looking at the monitor, then you're not going to waste your computation on fully detailing that object, because either the entire object or part of the object is not being seen by the user, right? But in order for you to know that, you have to basically run through the graphics portion of the of the application. And then once you get the results of that, then you know, okay, I just have to partially render part of the object, or don't render the object at all because it's not being seen, right? Because we're always in the business of saving computation, so you're not going to be computing stuff that has no real effect on you, the user, or on anything, right? You want to save. You want to save your battery, you want to save your resources, you want to save your computation, all of that stuff, right? So compute is also a consumer of graphics processes, right? It's a little bit harder to understand, but that is uh, that is part of the conversation. Now, real quick, I'll just transfer is just transfer, right? You're transferring stuff, like you're transferring stuff to, I don't know, to the CPU. You're transferring stuff to something else. You're transferring, right? That's easy. Sparse is just you partially bind um, something in memory, right? So you don't bind the full thing. You just maybe bind part of the thing that you really need to do processing on, but the other part that you don't really need to do processing on, you just put that in virtual memory, and sort of save on processing the full object. I guess if it's like a big object or something, that's, you could look it up online, but sparse is something to do with, like, just memory management and trying to optimize, not doing the whole thing, just doing part of it and binding part of the memory and stuff. um but for you video editing guys, you have video encode and video decode, right? So you hear people talk about, yeah, I don't want to use my CPU to do the video editing, I want to use my GPU, and oh my god, I use my GPU and it's way faster. This is where this stuff lives, okay? um this is where this stuff lives. Now, um really quick, there are some considerations in terms of hardware and how this stuff actually, why some things are able to be done, because you have, video encode and video decode in its own Q family. Okay, but we'll get to that in a second. Optical flow is just like motion, like pixels in motion. So, you know, uh, someone's running across the screen, or a comet is flying across the screen or something. Pixels in motion. Optical flow basically helps with, like, baking in additional frames to help with rendering the comet flying across the screen silky smooth, right? This is something where DLSS is used in, for all you gamers that use DLSS to upsample and upscale and all this stuff. This is where the optical flow thing comes in. um, and that's that. We have min image transfer granularity. So what's the lowest um, element? Like, you have pixels and then you have texels, right? What's the lowest element that you could truly transfer without losing fidelity or accuracy or all that stuff? That's what this min image transfer granularity is about. I don't know too much more about it, but that's basically all of them have that. Okay, and then you have timestamp valid bits. This is the clock. Um, how reliable can the GPU clock stuff? For the video encode decode, it's 32 bits or 32 whatever, and then for everything else, it's 64. This sort of has to do with profiling too, because when you're profiling an application, you want to make sure your clocks are correct and all that. So, not gonna focus too much on that. You guys could investigate it on your own time. Um, but all right, guys. This as you can see, this is what it is. This is the Vulkan API, but we have to get back to the hardware. Okay, so you have your GPU, your physical GPU that you bought from wherever you bought it. Some of you, it's hidden inside of your laptop. Others of you, you have an external GPU, or you built your computer yourself and you have this big brick in your case that's the GPU, right? So you could physically touch it. You could play, you could play frisbee with your GPU. You could play American football with your GPU. You could play anything with your GPU. You could kick it around. You could throw it on the wall, whatever you want to do. But the physical hardware is the real deal Holyfield. Okay, the physical hardware is the real deal Holyfield. The the Vulkan stuff is just abstracted from the physical hardware. Okay, so on the lowest level you have your physical hardware. On the highest level you have your Vulkan API, which is this stuff, right? The software stuff and all that stuff. There is a middleman between the Vulkan API and the low level hardware. There is a middleman. And this middleman has been the bane of everyone's existence, including the people that created Vulkan, or especially the people that created Vulkan. And every GPU manufacturer and everyone that tries to basically do anything with GPUs and stuff, and that middleman is called the driver. Okay? And the driver manages the relationship between it manages the relationship between the hardware and Vulkan. Okay, in the olden days it was OpenGL and the hardware, right? And before there was Tinder, before there was Bumble, before there was what, Hinge is the other one, before there were all these people, there was Driver. And the driver can be very problematic. Okay, so in the olden days when there was OpenGL and stuff, people would ship games and people would try, run their AAA game on their system, and every system had a different environment. And what would happen is that for some environments work beautifully, other environments works for a while and then crashes, and then other environments it don't run at all, right? And what the problem was that the drivers, right, the middleman between the hardware and the OpenGL situation, there was a problem because the code or the instructions or the information might have been interpreted differently depending on what GPU you had, what system you had, all of that stuff, right? So the situation became so bad that the Kronos group, which is in charge of OpenGL and now in charge of, and created Vulkan, they decided to create their own sort of driver language for shaders called SpareV. Okay, and you've seen me do this multiple times in videos before, where I have to compile shaders to SpareV so that we could run the application with the updates that I put into the shader, right? And literally, this whole language was developed in order to consistently manage the relationship between Vulkan and the GPU hardware. Okay. Similarly, here, this Q family stuff is trying to mimic what's going on the GPU. Okay. Now the thing is that with Vulkan, you don't. So we're gonna call the hardware or different pieces of the hardware. We're gonna call it GPU hardware engine. Okay, we'll just call different pieces of the hardware GPU, the hardware on the GPU hardware engine, right? So we have an engine for graphics, we have an engine for transfers, we have an engine for compute, we have an engine for a hardware engine for video decode, a hardware engine for video encode, and a hardware engine for optical flow. Okay? Now, let us dissect this further. Do you guys notice that when this is a modern thing, right? We never used to do this in the olden days. But you guys that play video games, right? You ever notice that when you're playing your video game, that you ever notice that like when you turn on screen recording, that your frames per second don't really drop too much? You ever notice that it generally stays pretty consistent with what it was before you turned on screen recording? The reason for that is because there is sort of specialized hardware that deals with video encode and decode, right? And what happens is that when you turn on screen recording, all video encode decode does is it just basically, the graphics hardware is spitting out these frames, and all the video encode decode does is consumes those frames. It could either consume the frame by getting pointers directly to the frames itself in memory, or it could do like a copy. So it copies the frames away from the graphics. So graphics produces it and then it copies the frames, right? So you have the transfer sparse stuff, right? You have the transfer sparse stuff. So what happens is that everything has transfer sparse, but basically you're basically just copying or getting the frames that the graphics engine is spitting out. So literally your screen recording operations is being done on separate hardware from what's happening with the graphics hardware. And that is why when you turn on screen recording, you do not get a hit on frames per second, not too much at least. Now, there might be other considerations like CPU stuff and the memory bottlenecks and stuff, but for the most part it's pretty seamless, right? And that's because you have dedicated hardware for your screen recording stuff. For you video editing guys that work in video production and video editing and stuff, this is why you want your GPU, because it does it really fast. Now, as far as the parallelism and stuff, I can't really talk too much about that. But notice that these dedicated video decode, video encode, and optical flow, notice that they have a Q count of 1. And part of the reason why these have a Q count of 1 is because this is specialized, is what they call fixed function hardware. Fixed function hardware means that it's very rudimentary, it's very basic hardware. You input one thing and you get an output, and that's it. It's not programmable. It's not programmable, and it's only slightly configurable, right? So literally, you give it what it expects, and it spits out its result, and that's it, right? These are what you call fixed functions. Okay, it's a thing in computer graphics and computing, fixed functions and mathematics, right? It's just in every generation of GPU they try to improve these fixed function stuff. But this is the reason why the Q count for these things is only 1, right? It's just you spit in something and you get something else. You spit in and you get something else, right? And it doesn't do anything else outside of that. So that these are why this is 1. Now, once we get into computation and we get into graphics and we get into transfers, notice that there's more Q counts available, because this is really what you're getting into with GPUs and stuff. You want to display stuff, you want to compute stuff, and you want to transfer stuff. Okay, but I say this to say that you, as the person that's running Vulkan and the author of applications and scripts, you don't have control over what you don't necessarily have control over what is done where on the hardware. You do not have control over that. So you could say, listen, I want to do some compute work, um, and you associate it, for example, with Q family 0, but it doesn't necessarily mean that the compute is going to be done on the graphics hardware. It could be done on the dedicated compute hardware or vice versa, right? You have no control over what hardware engine stuff is being done. Now, obviously, if you're talking about video decode, video encode, and optical flow, then, by default, obviously it's being done there because that's the only place it can be done. But as far as this mix between compute and graphics, you really don't have control. I don't know about transfer because everybody can do transfer, right? But there's an abstraction between Vulkan and the actual hardware on your GPU. You really have no control. All Vulkan can promise you is that, okay, you want this to get done, it will get done. But how it gets done is really up to the driver, right? And this is where things get sticky, and this is where profiling is so important, right? Because you basically submit stuff, and you can make suggestions, and you can give hints, but really and truly, it's the driver and things like that that make these decisions. Even if you go down to spare V, like, you're not gonna be able to like dictate stuff, right? You're not going to be a dictator in this game, right? Vulkan is a level of abstraction away from the hardware, and it kind of has to be. And the reason it has to be goes back to, again, portability, right? Vulkan is not designed for any specific piece of hardware. It wasn't designed for Windows. It wasn't designed for NVIDIA GPUs only, or it wasn't designed for, Apple M chips GPUs only. It's designed to work on everywhere. So because of that, Vulkan can't be so dedicated and restrictive and explicit about where stuff gets done. All it can do is give you a layer of Q families and tell you, okay, yeah, whatever, and wish for the best, right? So the thing is that this suggestion and this strongly hint and trying to get exact things to be done on the GPU a certain way, there's a spectrum to it. So Vulkan is probably the least suggestive. um, Next in line, that is slightly, ever so slightly more suggestive, and maybe you could get a better compliance, is DirectX. Reason for DirectX is because DirectX is, well, DirectX is by Microsoft, and Microsoft controls the operating system. Microsoft controls the DirectX language, and that about it. I don't think Microsoft makes GPUs. Okay, so it controls the OS and it controls the language, right? DirectX is Microsoft. All right, so slightly more. Next in line, we have a language called Cuda. Cuda is made by NVIDIA. So Cuda now, so the Cuda language is made by NVIDIA. The GPU is made by NVIDIA. The driver, um, I guess, is made by NVIDIA too. Yeah, the driver is made by NVIDIA. So you could kind of get a little bit more, a little bit more compliance with Cuda, right? Because Cuda is a high performance GPU programming parallel processing language. The language, the driver, the language, the driver, and the GPU is made by NVIDIA. Actually, for DirectX, of course, it's the operating system, it's the DirectX language, and the driver is made by Microsoft. So you get a little bit more. But then NVIDIA with Cuda is even more, because now Cuda is making, NVIDIA is making the GPU also. Right? And then you get to the most suggestive and the most sort of, you would say control, is the Apple ecosystem. Right? Now, if you're an Apple guy, you're singing praises, and if you don't like Apple, you're like, oh my god, right? But Apple Apple builds the computer, Apple builds the operating system, Apple builds the CPU, Apple builds the GPU, Apple builds the programming language you use, Metal, right? Um, Apple builds a driver. Apple builds the oxygen that is around the computer that is running. I'm just playing. Apple doesn't build the oxygen, doesn't create the oxygen. But what I'm trying to say is that Apple is fully vertically integrated. So you possibly could get away with more stuff with Apple. Okay? But just understand, guys, there's a level of extraction, not extraction. There's a level of, we're not mining. There's a level of abstraction with this stuff. Okay, and even though they market Vulkan as being very explicit and, oh, it's low level and you could optimize to your heart's content because it has the complexity and the boilerplate to prove it. When it comes to GPU hardware, it gets a little bit tricky, right? And that's pretty much it. Now you understand Q families, right? So, the fight generally is always between compute and graphics, right? That's where everything happens. But for you video editing guys, now you kind of understand what's going on here. Um, yeah, and that's pretty much it. I wanted to do this video again because I needed to do it in wide format because the one I have is not in the wide format. So anyway, guys, again, tutorial number 1, tutorial number 13. Tutorial number 1 installs the Vulkan SDK. Tutorial number 13 installs all these examples, including this one. Now, this stuff right here that we're doing, this is not in the example. Like the default compute input and stuff like this stuff is part of the example, but this stuff is like proprietary code that whatever, right? It's proprietary code that shows up all that's going on the GPU, right? So now you have a better understanding of what's going on. So you know literally the drivers. I mean, I know people like to give drivers a hard time, but they have a lot of work ahead of them. They have to decide, what queue family to do stuff. This queue family has 16 lines that you could submit. This one has 8. This one has 2. All that stuff. So the driver is very busy, right? It's very, very busy, and it has a lot of things it has to manage, a lot of relationships. So you think your relationship is hard? The driver's relationships are hard. Okay, I don't care if anyway, we're not even going to get into that. So people give drivers a lot of flack, but they actually play a very important role. And remember, it's not just one environment you're trying to manage. This stuff with. You're managing this stuff with every environment. So you know people give Vulkan a hard time, but remember, Vulkan is not tied to any one environment. It's platform agnostic, right? So you sort of have this abstraction and stuff, but it's for good reason. It's not for decoration. Anyway, guys, this is Cuda Education. Like, subscribe, tell your friends. Check out the descriptions below my videos because I might have additional information, including links to the original script that this is all based on. Um, Learn something in 2026. Time is expensive. Do not let 2026 go by and you haven't learned anything. Okay? Thank you for watching. Have a great day.